Thank you, Kiara. And also thank you to all the organizers, coordinators for a wonderful workshop and conference. I've already learned a lot. So I have to leave actually right after my talk, but I look forward to continue the discussion afterwards and throughout the whole workshop. So because I understand this is a highly sophisticated audience, I will be omitting a lot of the background information that I usually use to lay out the stage. And also thanks to a lot of the great talks before myself, I will try to avoid duplicating their information. Instead, I'll try to focus on the points I think worth mentioning. So I'm highlighting, so there are a lot of collaborators thanks to whom this work is possible. I'm highlighting the key contributors, including both highlighted in bold as well as in color, which are who are the early career scientists whose work I'll be highlighting in my talk. So let's jump right in. I'm sure you already know that the story of merger of supermassive black holes is highly twisted, so it's not a simple story. And just to remind you that I think Tamara already covered this point, but the occupation fraction of supermassive or intermediate mass black holes in particular is still highly uncertain. And this is especially true when you get down to dwarf galaxy regimes at high redshift, particularly relevant for LISA. I'm not gonna talk about this in my talk, but I have a grad student, Colin Burke, who is graduating next year and will be on the job market this fall. And I highly recommend you invite him to give a talk. He's a great speaker. And second point worth mentioning is even if you do have two black holes in both components in the galaxy merger, it doesn't necessarily mean a efficient merger just after two galaxies merge. So the usual impression is that there is going to be a bottleneck at the parsec-ish scale, which is the well-known final parsec bottleneck. But perhaps, as shown by most recent studies, there may be even a bottleneck at larger scales due to either tidal heating from nucleus stripping, which will make dynamic friction inefficient, or perhaps, as suggested by this 2017 paper, due to the unknown nature of dark matter particles, even some perhaps more exotic version of dark matter, such as the fuzzy dark matter, can even inject energy into a binary to prevent them from efficiently falling in. And finally, as we already heard from previous talks, so I won't repeat their points, but just to point out that the final parsec problem is not a problem unless you care about gravitational waves. So just really quickly going through, I think the current stage of, in terms of observational progress, I think a lot of new observations have been possible due to the progress in large surveys. And as you've already heard from both Julie and Tamara, so a lot of interesting example, either confirmed or candidates are currently known. So very exciting progress. But I wanted to point out two problems still. And the first one is for the confirmed systems. They still cover relatively limited parameter space, especially if you think about the quasar epoch, right? So around redshift 2 where the majority of star formation has happened, and perhaps the buildup of the bulk supermassive black hole mass it was happening. There is actually no confirmed case, even on kiloparsec scales, of a dual quasi in a confirmed galaxy merger. The other thing is, has already also been covered, is there's actually no confirmed case at sub-parsec scales. So in order to address these questions, so I'm gonna briefly talk about just two recent studies, projects. The first one is focusing on high redshift kiloparsec scale, and the luminous quasar population. And the other one more closely related to this workshop, concerning with periodicity and circumbinary accretion. Okay, so but before I go into the details, I want to make the analogy with exoplanets and stellar binaries. So there are a lot of inspirations from that community, and so basically a lot of interesting techniques, are connected. And in particular, I wanted to highlight astrometry, which is perhaps not so successful for exoplanets, at least not yet, but it turns out to be very useful for supermassive black holes. And so this slide just to give you just a background of the techniques that I think Julie mentioned early in the morning. And again, so all of these techniques have analogy with detecting exoplanets. And what I will be focusing on first is to use astrometry in particular. So before I talk about two supermassive black holes, I wanted to just briefly remind us about all AGNs vary, right? So we know there is typical variability on the order of 10% in typical, a quasar accretion disk, probably due to thermal instabilities from, a turbulent magnetic field. So this intrinsic stochastic, variability can be occurs later on, but in this case, it is a blessing to us. And the reason that it's a blessing is being illustrated here. So hopefully you can still see this cartoon made by Huang Xiangzhi, previous PhD student of Nadia Zakamska, currently an IAS fellow. So in this case, we don't actually have a resolved pair of double quasars, but because of their variability and the fact that we can trace their astrometry to much higher precision than you can by directly resolving them, you actually see this jiggling effect, which we term as vast astrometry, variability-induced astrometry jitter. So it's very similar to, just seeing this railroad crossing sign from a distance, right? So as the lights on both sides of the stationary signal, flash, you see this illusion of jiggling. But in reality, the scale that we're concerned with is still quite large, at least a few hundred parsec or even kiloparsec scale. So nothing is moving, so it's just an illusion. So using this technique, and thanks to the high precision of Gaia astrometry, so Xiangzhi selected these quasars that have these additional astrometry excess noise from Gaia, And with Tony, grad student at U of I, we are following up a sample of these high astrometry quasars, and indeed, as you can see from higher resolution follow-up imaging, at least it suggests that the technique is working, because you do see doubles, even triples or quadruples in this case of a strongly gravitationally lensed quasar at the bottom. And just to put them into the general context of the known examples, again, to remind you, previous work is relatively limited to low redshift, low luminosity, and or large separation. And with this new astrometry technique, we're able to, so I'm just gonna shift this particular example here, but so the red points are the ones that we are discovering with this new astrometry technique. And but a cautionary note is that there's still a lot of interlopers that you need to weed out using follow-up observations. And so you can have, projective pairs, you can have, star quasar superpositions, and you also have many strongly lensed systems, which are also known from previous studies at relatively larger scales. But the really exciting thing is that we are indeed finding these quasar pairs that are hosted by galaxy mergers at the epoch of cosmic noon, where quasar activity was at its peak, as well as the global star formation rate. So what I'm showing here is this the Hubble images of a particular example, where you can see is a really challenging task observationally, just because the quasars are significantly outshining their host galaxies. So in order to securely detect the host to rule out strong lenses, you need really highly stable PSF, such as with Hubble, as well as the high sensitivity to be able to see the faint host galaxies as well as tidal features. So I see that I'm already at my time, and so just quickly, I think I will skip these background. So just to point out that
you can have a few more minutes for the technical difficulty. Just you can gently wrap
sounds
up.
Great. Probably 3 minutes. So the final part of my talk is just to, I think, already pointed out by previous discussion, this periodicity expected from, I think, both 2D and 3D simulations of circumbinary accretion. And typically, if you have mass ratio bigger than 0.1-ish, you expect to see these periodicity. And a recent famous example is this quasar PG 1302, and being discovered and modeled by many in the audience. And what's interesting, I think, is that it motivated a lot of following searches, which has driven a lot of excitement. But obviously, the cautionary thing to say is, are these red noise or real signal? So to be able to, I think, get more cycles, not just 2 cycle for the majority of the candidates on the markets. So we're combining the dark energy survey with SDSS. So the DES is the closest thing perhaps on the market in terms of its depth. And in particular, as shown on the bottom, there are these 10 really, really deep fields that are reaching almost the depth of our SST. And if you combine that with SDSS historical light curves, only 2 of the deep fields have those, although. But you can do a analysis using really long-term, 20-year sensitive light curves. And from a parent sample of roughly 1,000 quasars to begin with, and we cut down to roughly 600, we discovered 5 possible candidates of strong periodicity. So these are all covering 4 to 6 cycles. But I should say that they are still highly subjective to red noise. So we're continuing monitoring them using DCAM now, and hopefully, in the near future, LSST will take over. And just to point out, a frequently asked question that I got was, well, is this contradictory to the PTA upper limits? The short answer is no, not necessarily, just because the fact that we are reaching fainter limits with DES, so we are actually sampling a different parameter space in the population of these supermassive black holes. So we're probing the less massive population at a given redshift. So to put into the context of gravitational wave sources, they are, because of their smaller masses, roughly 10 to the 8th, they are sitting in the gap between LISA and nanograv. So they are not in direct conflict with the PTA upper limits. So the final thing I wanted to mention is, I think most relevant to this conference is complementary evidence for circumbinary accretion, because as already been mentioned in this conference and in this workshop, is you can have perhaps X-ray access from shocks, from the mini disk interacting with the inner edge of the circumbinary disk, or you can have perhaps flux deficit or not from the thermal emission, just because of gap opening perhaps. And with a collaborator at default from Stanford, so we are we got follow-up XMM and NuSTAR X-ray observations, and we also have a detailed analysis of the SED. So I will skip the details, but the conclusion is that it's there has been some tentative evidence for circumbinary accretion, but it's still inconclusive. And this is also, I think, largely the case for the other candidates. And this is work being led by a former postdoc, Guo Hengxiao, now at UC Irvine. So what Hengxiao found was that for the majority of the optically selected periodicity candidates on the market, their broadband SEDs are very similar to normal quasars if you control luminosity and redshift. And even though there's a small fraction, about 5%, which could be due to a gap opening, but dust reddening and extinction is perhaps more likely explanation. The only, I would say, significant difference that we found between periodic quasars and normal quasars is, some tentative evidence for a higher fraction of, highly radio-loud quasars or blazars in periodic quasars, and these could be due either due to jet precession, perhaps contributing to the optical emission, or it could also be due to a large fraction of red noise, just because of the higher fraction of variable sources. So that's my all of my talk, but I know it may sound a little bit discouraging, so I wanted to end on a positive note, and just to leave you with some, I think, better examples of periodicities that have been recently discovered. The first one is an optically detected source from Assassin, so Assassin 14KO, and in which you already have, I think now, as of the time we speak, like more than 20 cycles of the burst being covered. So it's highly significant, unlikely to be due to red noise. And at the bottom is a quasi-periodic eruption, two of them actually, from E Rosita. So the bottom two are on much shorter timescales. I won't go into the details of the physical origins. I think they are still being debated, although the leading hypothesis for Assassin 14KO is a partially disrupted tidal disruption event, and for the E Rosita sources are perhaps these extreme mass ratio in spirals. But I think their origins are still debatable. But the bottom line is that I think it's still hopeful to find robust periodicity signals as long as your data is good enough. Okay, so here are my take-home points.
Okay, let's leave these on the screen so that we can have time for some questions, because you've said so many interesting things. I'm sure that there's a lot of questions for you. So we have a couple of minutes for questions.
Maybe quick questions, yeah.
Okay, thank you so much. Let's thank Xinlu. Okay, questions from the audience. Okay, while you're thinking about your questions, I can, oh, Zoltan, you have one?
Hi, Chin, thanks for the nice, nice talk. Very nice overview. If I remember, the rate of the binary candidates you find, they're higher than in other surveys. I don't know if you can comment on what might cause that.
Yeah, absolutely. So the rate that we found from the DSD field is, roughly, 4 to 80 times higher than previous estimates based on CRTS and, PTF. But I think if you notice, because they are very different surveys, with very different data qualities. So ours is really like tensor beam surveys, and whereas previous candidates are from these shallower surveys of large areas. So I think they may reflect the fact that we are really probing different populations. But it's also possible, I think both studies are still highly subjective to red noise contamination.
Are there any other questions? Yeah.
So this is sort of this is Caitlin Crowder here. Sorry, and this is another naive star person question, but following on this question about the agreement in the rates, to what extent is it possible to do a careful selection bias analysis so that what you expect? If basically if these are probing a population that's, say, consistent with the cosmological simulations or something like that, what do you expect to recover based on resolution, sensitivity, mass ratios, things like that?
Yeah, that's a great question. I think when you do a comparison, it needs to be tailored so that you're matching all of the selections that you mentioned. But this is very challenging to do, as I'm sure you know that. So there has been a work, I think pioneering work being done, but I think still more work is needed to do these more tailored comparisons in order to, I think, really understand what the implications of the race really are. And perhaps I think more importantly is that we still have that big question mark about red noise. So I think it's perhaps more important to be able to pin down the first order question. Is that red noise or is that the real signal? Because as I show at the end, once your data is good enough, it's definitely possible to answer that first order question. But the second order question is, so are they really binary due to binary supermassive black holes? And the answer is, at least for these, I would say highly robust periodicity candidates, equal mass or roughly equal mass binary supermassive black hole is not the leading model for either of these.
I guess I was just to clarify, I was just asking whether or not, is it obvious that it's easier to rule out red noise in isolation, or is understanding what you might expect between two surveys, like is a comparison between two surveys another way at getting at, some set of them being likely red noise versus not?
Right, yeah. The difficulty with that comparison is, so because different surveys, they are sensitive to different parameter space, in terms of the populations, you need assumptions to extrapolate from one to the other.
Okay, well, let's thank Xin again. Thank you so much for an interesting talk. I didn't get to ask you my questions, but I'll send you an email because I have so many.
Yeah, absolutely.
So
please feel free to follow up. Thank you.
Wonderful. Let's thank the speaker again.